Welcome to NASA Science Live. I'm your host, Tahira Allen. Today, you'll have the chance to meet and ask questions to scientists who venture into Earth's most extreme environments to help humanity explore farther into the cosmos. Have you ever wondered, how do we prepare to explore places humans have never been before? Where should we even search for signs of life beyond Earth? And what are we doing to prepare for our next frontier, the Moon and then Mars? If so, you're in the right place. The journey to answering these questions begins right here on Earth, where our planet's most extreme environments are used as testing grounds for future missions. During today's show, you'll have the chance to ask your own questions and hear directly from our experts about how their expeditions are preparing us to explore the Moon, Mars, and beyond. You can drop your questions into the comments wherever you're watching or use the hashtag AskNASA on social media. Now, studying other worlds may sound like science fiction, but it often begins in some of the most breathtaking places right here at home. Recently, NASA's Goddard Instrument Field Team traveled to Iceland, a landscape shaped by fire and ice. Its rugged terrain makes it an excellent training ground, mirroring many of the conditions scientists will encounter on the Moon, Mars, and other worlds. By investigating these analog environments, our scientists are learning how planets work and paving the way for Artemis missions that will return humans to the lunar surface. Coming up, we'll meet some of the team to take your questions live on air. But first, let's take a look on the ground in Iceland.
So we just hiked up the slopes of the Hekla volcano in southwest Iceland. This particular site is important for lunar research. The regolith on the lunar surface is pretty fluffy, and we think there could be small grains of water ice hosted within that. So today we have a few of our teammates setting up some ground-penetrating radar surveys, and what it does is it makes a 2D slice of the subsurface, and we use that to understand what sort of material we're looking at.
Look at those reflectors.
Oh, yeah.
Let's go look at ice grains. We brought in an auger to drill down into the subsurface to confirm our observations.
Auger in hole.
So that we can actually ground truth the observations that we make with the GPR.
Yeah, and you can see the sparkles of the ice.
That's a gift shot.
Yeah.
That's really...
Nothing can a Mars polar scientist more exciting than ice crystals. Ooh, I'm so excited for show and tell.
We have something to show.
So we're gonna drill through the snow and look at the transitions from snow to ice to volcanic sediments. We'll get going. Hopefully we'll see some ice-cemented volcanic sediments, and then we'll see how deep we can get.
Yeah.
Yes!
Yes! And so a lot of the ice, as we move through here, has different characteristics. Some of them are just filling tiny pores. Some of them are actually cementing it. As they look for ice underneath the surface, what I am trying to do is learn to characterize that ice and do that using visible imagery like cameras and how best to capture them to help learn how we can prepare our astronauts in the future. I'm just really excited about the prospect of doing actual geology on the surface of the Moon and as we work our way toward Mars. So it's really a dream come true, and I can't believe I'm actually going to be a part of it. And so I'm so excited.
I'm joined now by Emily Shoemaker-Thaxton, a planetary scientist who you just saw on top of an active volcano in Iceland. Emily, that's amazing. So cool. Thank you so much for being here with us.
Thanks so much for having me.
So again, we just saw you on top of an active volcano doing science. Can you kind of put us in your shoes? How was that?
Yeah, it's really breathtaking when you get to the top of a mountain like that and you're looking down over this unvegetated landscape, and that looks a lot like Mars or what the Moon might look like. Yeah. And you can really just put yourself in the shoes of the astronauts, or boots, I should say, on the surface of those worlds when they go out to explore them in the future. So for me, that was the most exciting part.
Yeah, I mean, it really looked otherworldly, which is amazing. So can you you remind us, what was it you were there to do, and what were you trying to learn?
So we went out into the field with three main objectives. One was to think about how much ice there is and what it looks like, and then can we actually measure that with the ground penetrating radar that you saw in the video, so geophysical instrumentation. And then we were interested in how deep it actually is. So is it accessible for future astronauts? And we did that with a variety of tools, including the GPR. We also you saw our drill and auger where we were pulling up samples of ice from the subsurface. And then we were imaging all of our samples with a camera and trying to understand how astronauts might actually do this on the moon when we get there.
So you really were putting yourself in like the boots of the explorer. So you mentioned GPR. Can you tell us what is that?
So GPR is ground penetrating radar. It's an electromagnetic geophysical instrument. So what that means is we're actually sending microwaves, like you might have in your home, down into the subsurface, and that bounces off of different materials, and it returns to the radar system at different speeds. And from that, we can actually know what we're looking at in the subsurface.
That is so cool. Now, I have one more question, but I want to remind our viewers at home, start sending in your questions for Emily by dropping them in the comments wherever you're watching, or send them in using #AskNASA. Now, Emily, again, you told us about what you were doing, what you were hoping to find. Can you help explain, how will this help our future astronauts? Are they planning to do this on the lunar surface one day?
Yeah, so the tools that we had out in the field with us, we were actually trying to think about what they would really have on the surface. And several of those they probably or possibly will have. So there's actually been a type of ground penetrating radar selected to ride along on the lunar terrain vehicle, so the cart that the astronauts will be riding around on the surface, that can help them do their surveying. And they also might have access to things like shovels or drills and retrieve the samples. And they'll certainly have cameras. So we were trying to really think about what they're doing on the surface, how they'll do it, and what would be most helpful as we look for this buried water ice.
Amazing. So I do have a question real quick from Emily F. on YouTube, who asks, wow, this is so cool. How often do these teams go into the field, and do they study or learn different things depending on the time of year?
Oh, yeah, certainly. So that's a great question. Our particular team tries to go out maybe once or twice a year. We usually try to go in the summer just because that's safer for us in these really cold environments. Iceland can be really snowy and dangerous in the winter, so we tend to go out when it's a bit warmer. But you definitely learn different things at different times of the year, and the season sometimes might correspond to what we think other planets might be like. So the analog could depend on the time of year, too.
Amazing. So I have a great follow-up question. It's from Guy the Dude Human on YouTube, who asks, do you guys at NASA always go to Iceland to prepare for space travel, or do you visit other places? And if you do, what are some examples?
Yeah, great question. No, we don't only go to Iceland, though I will say Iceland offers one of the better, really accessible analogs for us. But we've gone to other places like the Valley of 10,000 Smokes in Alaska, which is a very remote location on the Katmai Peninsula in Alaska, where we were looking for actually similar questions. Some people were looking at the volcanoes that were there. My team was looking at buried ice, as you can imagine. So we go all over the world. There's really no limit to what a good analog might be on Earth.
Is it just a coincidence that was also a volcano? Is there a correlation between volcanoes and looking for water ice?
No, that was just a coincidence. Just because of the climate there, it's very similar to Iceland, so it just happened to be a good spot.
Awesome. So we have another question from AskPlex on X, who asks, are Earth and Mars made? Basically, do they have the same materials? And I know a little bit earlier we were talking about your instruments could also apply to finding water ice on Mars. And so could you talk a little bit about the potential of water ice on Mars, if that's a thing that future explorers could actually look for?
Yeah, certainly. So, yeah, there are similar composition rocks to what we might find on the Moon or Mars. And so in some cases, depending on what your science question might be, you might want to look at that. And can you remind me what you wanted me to address too?
Well, yeah, so right now you were looking for water ice, but for the Moon aspect, is that something that future astronauts could discover on Mars, too?
Oh, yes. Yeah, thank you. Yeah, there's certainly a lot of water ice on Mars, and we've actually been mapping that for decades now using orbital radar instrumentation. So we actually think there's many meters of ice buried at different latitudes on Mars, and certainly you have 2 polar ice caps on Mars, very similar to Earth.
And so when you're looking, even in your experiment for Iceland and the moon, are we looking for, like, big pockets of water ice, like cubes, little grains of ice? What are you searching for?
Yeah, good question. So that's definitely something that we're hoping to learn more about when we get to the South Pole of the Moon through Artemis. But I think right now we're expecting we might find something like grains, maybe like similar to what we were actually seeing at Hekla in Iceland. But there is the potential for many meters of thicker ice to be buried in the subsurface too, but we don't think as shallowly as maybe what the astronauts could access.
Cool. So I have a follow-up question from Ravi on X, who asks, how do these analog sites help prepare for future missions to potentially icy moons?
Oh, okay. Icy moons. There's going to be some later talk about that with one of the other guests on the program, but certainly there are sites on Earth that we could go to think about what icy moons might be like. Maybe for our robotic explorers first, because that tends to be a really, really extreme environment. But you could go to places like the Arctic or Antarctica to explore questions about icy moons, and there are teams doing that right now.
Do we think that our own moon has a lot of water ice potentially available on it?
Yeah, I think the thought is that there is a lot of water ice that we could access, especially at the poles. But there's other ways that the moon gets water delivered to its surface. So you can actually get little molecules of H2O forming from the deposition of hydrogen through the solar wind and things like that. So you actually might have a bit of a larger water reservoir than you'd think.
And can you help us understand, why does that matter? Like, why are we interested in looking for water ice on the moon?
It's really important for humans. We can do all sorts of things with it. I mean, most importantly, it's the water we drink, but it also can be things like fuel for our spaceships and rockets. And as we make our way toward Mars, we need to understand how we can use that water to sustain our presence on the moon, and then how we'll use that going forward when we explore Mars. And hopefully we have access to more water there.
Yeah. I mean, water is life. So it makes sense that we're looking for it in all of these faraway places.
Yeah.
And so, actually, a great follow-up is from Brian on Twitch, who wants to know, what signs could an astronaut actually look for when they're trying to find water ice on the surface of the moon?
Yeah, so that's a really tough question. When we were in the field, you didn't necessarily see that the water ice was present at the surface. So we needed to use our geophysical instrumentation to be our eyes in the ground.
These are the microwaves.
Yeah, the GPR. So we were using that to see into the subsurface, and then we knew where to target to drill and retrieve samples. And we think the astronauts are going to have to do something pretty similar. You won't really see a block of ice sitting on the surface of the moon. It's got to be protected by the lunar regolith.
So I guess the answer is really by using the technology that your team is testing, which is cool. Our next question is from Sizane on YouTube, who wants to know, what is the most interesting thing you think we could find on the moon?
Well, I'm really biased because I find the water ice question to be really exciting. I just think that's so exotic on a body like the moon. But I also am interested in volcanoes, so I'm very excited about any mission that might go and explore the volcanoes on the moon. Perhaps something like the Gruithuisen domes or lava tubes on the moon. Those are also really exciting.
Awesome. Our next question is from Mikey16 on YouTube, who asks, will this help future astronauts like on the Artemis 3 mission?
Yeah, certainly. So a lot of our research is thinking about how astronauts are going to work on the surface. Artemis 3 is kind of one of our first jumping off points of doing that, and hopefully it'll set us up so that we have a better idea of how we're actually going to do water ice retrieval on the surface of the moon long term as Artemis continues.
So Emily, how did you even get into this kind of science?
That's a good question. My path wasn't always like direct into science. I started out as a person that really enjoyed like music, and so I thought I was going to go to school for that, and then I decided to go to school for physics, and I did my first astronomy project looking at the Milky Way galaxy and mapping that with radio waves. So very similar to ground penetrating radar, but looking up at the sky instead. And then I got very interested in Mars after that, and the rest is history.
Wow, amazing. And then now the moon.
Yes.
And so that's awesome. So we have another question from Annabelle, who asks, what are you hoping to find on the moon or Mars? I think you alluded to this a little bit earlier, but again, can you expand, what is the big focal point for your team? What would be a win for your team and the work that you're doing when it comes to these two planets?
Yeah, I think, so for the moon, I think it would be really exciting to just be able to locate buried water ice rapidly and have it easily retrievable for the astronauts. So I think that's like the big goal. And if our research can make that easier and help them do that quickly, then I think we've achieved our goal. And for Mars, the longer term goal is thinking about bigger reservoirs of water ice. It's just as hard to get to. So thinking about how are we going to extract more, what does that look like, and how are astronauts going to expand their presence on the surface of Mars in the future to do that.
I have a question from McFlurry Mac on Twitch, who asks, how are we sure that the ice on the moon is actually ice?
Well, that's a good question. I think, we have to be patient and maybe wait until we get to the surface to confirm that 100%. But we've had a lot of orbital instrumentation show that what we are finding is indeed water ice. We had the L-Cross impactor actually hit the surface of the moon and release some of that water ice into space, and then we measured.
We're pretty sure.
Yeah.
Okay, awesome. And so, Emily, too, you were talking about your work and you were identifying where water ice could be, but did your team also, test how you can retrieve it?
Yeah, a little bit. I would say we were mostly retrieving it for ourselves to make sure that what we were looking at in the subsurface with the GPR was indeed there. So we wanted to make sure what we were looking at was ice. But certainly there are drills in the works to be deployed on the surface. So the auger that you saw in the video could be really similar to something that might be used in the future.
Well, so cool, Emily. I hope your research and your science makes it to the moon one day. Thank you so much for being here with us.
Yeah, thanks so much for having me.
And now let's venture further out into our solar system beyond the moon to a world that we've had our eyes on for a very long time. From orbiters to landers to rovers, we have been studying Mars for decades. But there is still so much left to learn. Now, believe it or not, Iceland is also home to rocks that are very similar to those that our rovers and future humans will study on Mars. Let's go along to another team on the expedition to see how Iceland can teach us about the red planet.
Tell me when. You want one more?
Let's go one more. I'm David Burt, part of the SWIFT mission. We're here at Lake Kleefervaten looking for carbonates and some other carbon-rich species. We don't understand how the carbon cycle works on planets and planetary bodies beyond Earth. Iceland and Lake Kleefervaten as a whole provide a really nice analog.
I'm Mike Thorpe. I'm an assistant research scientist at the University of Maryland and NASA Goddard Space Flight Center. We're at this region called Stora-Laxá, which is in the southwest region of Iceland. It's a river that is kind of carving through these basalts that were laid down by volcanic activity. So our goal is to kind of look at the change of like how you go from sediments in a stream to kind of a sedimentary rock and what happens in between. They're widespread on Mars. I mean, it's almost all what Curiosity has looked at is rocks that were formed in a lake in rivers. But really, as one-to-one comparison as I've come across. So excited to get our hands on it.
We're pulling a mix of samples here. We're getting gases, we're getting fluids, we're getting sediment core samples. It's called the heart, in part because of its shape. It's a relatively shallow spot. You've got CO2-rich bubbles coming up out of this loose sediment. There's a ton of information to be interrogated here. What does life need to operate? And we're particularly focused on carbon, since that happens to be one of the big elements that underpins life as we know it.
We came across the perfect outcrops for me. We were seeing these kind of siltstones, the mudstones, so they're really fine-grained material, which are perfect because those are deposited in like a lake environment, so a very habitable environment. This is super exciting for me. This is, I mean, we've been looking at sedimentary rocks that have been formed in similar processes on Mars. It's really cool to be holding a piece of information like this.
I come back to the idea that the average landscape around us can tell us so much about the world we're currently living in, the history of our planet, and other worlds as well.
From beneath lakes to the peaks of mountains, it is incredible to watch these scientists in action. And I'm joined now by one that you just met in the rain and fog of Iceland, Michael Thorpe, a sedimentary and planetary geologist. Mike, that looked like quite the expedition. Excited to get into that. Thank you for being here with us.
Yeah, thanks for having me, Tara.
So earlier before we were talking, you mentioned that this is not your first time out in the field. Can you give us an idea of some of the places you visited and what you were studying?
Yeah, so field geology is kind of the reason I got into this profession in the first place, and so I'm excited to be out there. That's my happy place. I started out in Long Island during my graduate studies and then made it all the way west to Hawaii and hit a bunch of places in the States in between. I've gone abroad to Lanzarote, Spain, Turks and Caicos. I've been to Hawaii a couple of times, so a bunch of different places that I've been super fortunate to go to.
And so why these places, though? Were they similar to, I guess, other places NASA was trying to study in the solar system?
Yeah, so every analog, there's no perfect analog is the thing. There's nothing that matches Mars here on Earth, but we try to target specific features or processes that we try to understand better here on Earth to apply that to other planets too. So each of these places offers something unique that I can learn something about it and apply what I'm learning here in the terrestrial environment to what we're seeing kind of in a Martian environment as well.
And that's what you were doing in Iceland, right? So we saw that your team discovered these amazing mud and siltstones. Can you tell us how these rocks in Iceland are helping us learn things about the rocks on Mars?
Yeah, so being up and close and personal with these rocks gives us a really good idea of how they formed, kind of what climate they were in, and so we use what we see on the ground in Iceland and compare it directly to what the rovers are seeing. So the rovers are akin to our kind of geologists on the ground there, and all they've been seeing are kind of these mudstones and kind of river rocks as well, and so these things we know form in those kind of environments, and that's why we're trying to tackle those in Iceland. And it was really a remarkable comparison. It was the best, I mean, I call it my #1 outcrop that I've been to before. And that's,
really?
Yeah.
Oh, my goodness. And so, you know, what do you think is the most important part then about going into the field and doing science like this?
I mean, so for instance, if you're looking at Google Maps, like you get a good idea of what's going on from above, but when you're out there getting your hands dirty, literally getting your hands dirty in the field, you learn so much more about what you're looking at there too. And same thing goes with Mars. When you're looking at remote sensing data, you can learn a lot, but when you're on the ground with the rover, you learn so much more. So actually having these samples in hand gives us kind of a different piece of the puzzle that we wouldn't have otherwise.
Cool. Now, we've got a ton of social questions coming in, so I'm going to get to those in just a few minutes. But again, as a reminder for those tuning in, feel free to drop your questions for Mike into the comments wherever you're watching, or use the hashtag AskNASA on social media. Okay, let's see what we have coming in. So we have Ya Empress on YouTube who asks, what limitations do Earth-based test sites have compared to real conditions on Mars?
Yeah, we always have to kind of do the pluses and minuses what one analog provides versus another analog. So, for instance, I've done a bunch of field work in Iceland where we're looking at modern sediments that are in the river, but everything we're looking at on Mars is lithified. And so the limitation there was like these rocks have experienced some compression and things over time that changes composition. this time I was lucky to actually find those rocks there, but it's also different atmospheres that we're dealing with. Sometimes it's different kind of starting materials that you're dealing with. Sometimes it's more rain.
Yeah.
Sometimes there's vegetation. You just can't get away from that on Earth. So that's why we go to all these different places to kind of piece together a bunch of different pieces of the puzzle to kind of understand it all more, a comprehensive story, if you will.
Yeah. And so when you say lithified, can you break that down for us?
Lithified is just taking sediments that are out on Earth here, whether it's like dirt that you're literally out there or on the river itself, and just compressing it. And so over time, you really are just compressing and smushing it into a rock itself.
And so does it matter either that, you know, these rocks on Earth are a lot younger than the rocks that we're seeing on Mars? Does that...
Yeah, it definitely matters. It changes some of the minerals that I look at, but it's also pretty remarkable. I'm actually quite shocked how similar the data that I've been seeing from some of these trips are similar to what we're seeing from the Martian rover. So that shows that something unique happened in Mars to kind of preserve this early signature. So even though the Martian rocks are quite old, they're ancient, they have a lot of similarities to what we're seeing here on Earth.
Cool. Now we have Annabelle X on YouTube who asks, what are you hoping to do with the data that you collect from, you know, the moon or Mars?
Yeah, so for me, I think it's kind of guiding future exploration too, and/or kind of putting together a reference frame for what the data coming back from the rovers are. And so it's hard to interpret the data without having a complete picture. The rover can only drive so far. When I'm out there hiking in Iceland, we're going kilometers, and we're out there for 8 days at a time, and we really are really at a good pace. Rovers can't do that. They're a little more restricted too. So we kind of provide that bigger picture, kind of broader view of what's going on by placing the stuff in a context. And then outside of that, we can kind of use our knowledge base to kind of say, like, this was a good sampling spot. Maybe you should go over there. So, like, learning where you might sample, targets of interest are definitely important. And then if you take that a step further, kind of teaching astronauts how to be sampling in the field when they go on to these other planets or the moon, you're only dealing with rocks up there. So the geologists are hopefully helping guide where you might go and kind of interrogate.
Cool. So it's like an assist. Like y'all are working together, and then you're kind of like providing them the direction our way.
I love that. I'll take that.
Yeah, that's cool. All right. We have Jared Banque on Twitch who asks, what does a typical field survey look like? How much ground does it cover, and how much time?
They're all different. With that expedition in Iceland, and tip of the cap to all my teammates who were out there, it was really fun being with all them. But there were 8 different expeditions going on. You saw people scuba diving.
Yeah, at one time.
Yeah, their trips looked fundamentally different than my trip, where I was just hiking kilometers at a time. And so my expedition kind of targeted something different. We were hiking along this river, and so we were really looking for these specific outcrops, whereas there was other teams that were, like you heard from Emily before, looking for buried ice. So every expedition is different, and even on those expeditions, the science investigations on them are all different too.
And so I have a great follow-up. We have Carolina Sanchez on YouTube who asks, you know, if you were able to get a direct sample from Mars, what kind of insight would that provide? You know, what parameters would you be interested in?
Great question. That's exciting to think about, and hopefully we get those samples back one day. But I look at the alteration minerals, and so that's things that form. So you have minerals that form from the lava itself, but then as you weather them, just like we weather here on Earth, they change their composition, and those minerals kind of tell me exactly what the climate was, how much water was involved, and so I can use all those as kind of unraveling the history of that rock itself. And so I think we talked about it before, but every rock has a story to tell, and that's compelling to me. So I look forward to kind of telling that story.
And it's amazing too. What you were just talking about is that you can read just different signatures in a rock and know that, hey, it went downstream from a river, or, you know, it was in a dry location. Is that similar to kind of how our rovers are studying Mars right now?
Yeah, absolutely. I'm pretty nerdy about that. That may be my dinner table talk about what this mineral might tell you or something like that. But yeah, it definitely tells us that. And so when the data comes back from the rovers too, that's exactly what we do. We meet as a whole group and we discuss what's going on there, and kind of everybody's got, you know, their own opinion on it, and it's nice to work collectively as a team to kind of see what fits in the end.
So I have Yaw Empress on YouTube who asks, what skills or degrees does NASA need most for future missions? And so maybe you take this in the geology
Yeah, sure. I mean, like we always need to keep pushing the geosciences. Like I said, when you're up there, you're just dealing with rocks, and so we need to understand the fundamentals of how those rocks weathered, how they formed today, what's happened with them in the future. Are there reservoirs for important minerals that we're looking at and stuff like that? So definitely geoscientists, but then engineering is obviously. I mean, working with engineers on the rover teams are amazing too. So I think those are two huge applications that we'll need in the future.
How did you even get into this, becoming a sedimentary planetary geologist?
I grew up just loving to hike. I was right on the Hudson River in New York, and I would go hiking daily, and it's pretty funny, but my sister told me at a young age that those rocks do have a story to tell, and like
Cool.
that stuck with me. I just used that example a couple minutes ago, but that's what got me into geology, and I was like, I want to know that story. I'm going to figure that out, and I kind of just went down this pathway and loved it ever since, so I'm definitely lucky to have the career that I do, and lucky to be doing it for NASA.
Well, shout out to your sister, you
Yeah.
know, like like getting you starting from rocks to all the way like studying rocks on Mars. That's so cool.
Yeah.
Our next question is from CapSam1 on Twitch, who asks, Does Mars have alluvial fan debris fields like we do here on Earth? Have we compared their behaviors to ours?
Yeah. I think they may meant to say alluvial fans, and that's what kind of happens when you have just like streams that are coming down a mountain, and it kind of quickly deposits everything quickly, and it makes this like fan shape. And so it's pretty, I mean, it's gorgeous to look at, and they do. And so that's a good question, and like that's why we went to Gale Crater, where the Curiosity rover is, because it had this alluvial fan. And it's kind of a similar, different depositional environment, but deltas where the Perseverance rover is right on a delta too. So that's kind of when a stream goes into a body of water too. It makes a fan shape as well, but just a different kind of shape overall. So we definitely target these environments that we think were habitable or definitely had water active in it at some point in time.
Cool. Now, Emily F. on YouTube asks, what would you say is the most exciting thing that you've studied in the field that was later utilized by an astronaut or other researchers?
Well, I hope my stuff is used by an astronaut one day,
Yeah.
but I can't say that yet. But I think we've been focusing on a lot recently where groundwater goes into a lake, and so you kind of don't see. We call it this invisible component. It's kind of going through the sands and making its way down into the lake itself, and that mixes with the lake water too. And when that happens, there's these really unique chemical reactions that go on and change the mineralogy of the rocks themselves. And we can uncover that with the things that we've been doing here on Earth. And so I've applied that, and other researchers have applied that to kind of some of the rover results to be like, yeah, maybe this happened on Mars too. And so we're trying to dig into that a little more too.
Wow, and really just build this picture of like Mars's wet, watery past
Yeah.
and how that relates, I guess, right, to Earth eventually.
Yeah, absolutely.
So I have a fun question. It's McFlurry Mac on Twitch asks, if you could add one instrument to the next rover that would make your life easier, what would it be?
I'm always going to be a big proponent for an X-ray diffractometer, XRD. And
Oh, wow.
that just really...
Sounds so sci-fi.
Yeah, it definitely does, but that's what tells us about the minerals. And there is one right now, the Chemin instrument on the Curiosity rover. I think it's just remarkable, the data that keeps coming back from that. It's a gift that keeps giving, and we learn so much from it. I think the mineralogy is super important to understand. It's very fundamental to kind of knowing the history of the rock itself, putting all those pieces together. And so I'm definitely a big advocate for those instruments. That would be my number one.
Cool. So we have Ryan Quinn on YouTube who asks, how will current research on Earth's frozen water and sediments guide the design for future missions to the Mars or maybe even Europa?
I think it may help us understand what kind of instruments we need to unravel what the science is telling us about there too, but it also kind of helps us with engineering, like how do we sample those things in these cold environments too? Emily, you saw in her video the drill before, how do we dig down into these too? It's not as easy as it looks too, and I've been out in Iceland too with drills where we've failed.
Do they break or?
Yeah. That's the thing with fieldwork. You always got to be able to adapt adversity or you're in trouble. So, these drills, they break occasionally, and you just need to kind of find techniques that work. You need to be able to roll with it and figure it out real time. So I think these hardships in the field kind of guide us to how we might be able to do future missions and stuff like that.
Well, I think that's such a cool concept, too, because, again, if we're preparing for our future explorers on the moon and Mars, they're not going to be able to just run back down to a lab and get a new instrument. And so do you have a time in the field where you've maybe had to pivot and your drill breaks? What do you do next?
You just gotta roll with it, and if you don't, then your mission's gonna fail. So, for instance, a couple of field trips ago, we had this pump that got wet, and instead of just rolling up shop and coming home, because we were out there for 2 weeks, we developed a hand crank for getting the water out of the ground. Then we didn't know was actually gonna happen in that fashion, and so like. You have to learn real time, and that's where your teammates come into play and stuff like that too. And it's just like you definitely need the support out there to be thinking as a unit.
I have a question from Carolina Sanchez on YouTube who asks, what kind of instruments did you use to study these Icelandic rocks? And what information do they tell us?
So we did use an XRD, like I said before, which is
XRD?
Yeah, XRD is an X-ray diffractometer.
Oh,
yeah, it just it just shoots X-rays at it. It's like if you were getting your arm or your teeth X-rayed at the doctor's, but it tells me the minerals instead of like show me where your bone is. So it tells me the minerals. So we did have that. Like this one was like in a little suitcase and it was portable. So we took it out into the field and we opened it up and then analyzed the samples there. So that told us the minerals that we were looking for, and that actually helped guide what we were looking for. But we also, various teams had handheld instrumentation that tells you the elements that are in there. And so instead of the minerals, it's telling me the elements. Other teams are looking at it. You heard Emily's GPR before, trying to locate ice and stuff like that. So there's a bunch of different pieces and different instruments that help you paint that bigger picture of what the geological history is going on in that environment.
And so the instruments that your team was using in the field, are these types of instruments that we could see future explorers using?
Yeah, absolutely. Some of them, we specifically target some of them because they are currently or akin to what might be on the rovers themselves. But there's definitely, colleagues who talk about using these various instruments for astronaut exploration. And that's a big component of our research too, is to see how we might be able to implement that in the field. How does that guide what you're going to be sampling? Are you looking for just that shiny rock, or are you looking for a particular set of elements or minerals or something like that?
And so I have time for one more question. I have a follow-up from Ryan Quinn, who wants to know, how does studying rare rock types on Earth, like the volcanic basalts or impact craters, help us interpret the samples that we collect from other planets or objects in our solar system?
Studying the igneous rocks themselves, so those volcanic rocks are going to tell you like how quickly that magma cooled, or how quickly or where it cooled in the system, like in proximity to the surface. But then for me, I'm a sedimentary guy, so that means that we take those rocks and we beat them up and we move them downstream. And so like I can tell you how far it was moved downstream. I can tell you the composition of the water. Was it really salty water, or was it kind of very neutral lake-like water or something like that, fresh water? I can tell you the climate that it was forming in. I can tell you.
It's incredible.
Yeah, so there's a lot that you can unravel just by seeing the composition of that. So that's the fun part.
And just by reading a rock, which is so cool.
Yeah.
Mike, thank you for being here with us. Cannot wait to see what expedition you're on next.
Appreciate it. Thank you for having me.
Yeah. Now, on Earth, water plays an important role in the origin of life. And our planet is not the only place in our solar system that is home to water. Jupiter's moon Europa and Saturn's moon Enceladus have evidence of vast underwater oceans that could be excellent places to search for life. Now, as you'll probably guess from this show, Iceland is also a great place to work towards understanding these watery worlds right here at home.
I love exploration, being a part of NASA and being a part of the work that we do. Coming to these environments to understand how Earth can inform us about these really distant places, it's really satisfying. We are interested in the CO2 that is bubbling up from the vents in the center of the lake. Iceland is a place where you can actually access the carbon coming from the Earth. And when we go to other planetary systems, one of the ways to understand whether life could ever be present there or even is present there is understanding the cycling of carbon in systems.
This is a rift zone. This is actually where the continental plates are breaking apart, and you have magmatic fluids coming up through that.
There's quite a bit of wind today. We are going to wade out to a vent.
We're going to be walking through the water and we're going to be collecting samples. So we'll actually have a probe that allows us to produce a transect so we can walk out to it and say, oh, how's the environment changing as we approach this particular vent? So I will be performing scuba diving to collect the gases in those samples. We'll do that probably in two ways, one of which is that there's so much gas that we could actually turn over a bottle underwater and just let it fill. We're also collecting some sediments just so that we understand like what is the actual carbon that's already in these rocks. Feel this core, it's actually like really nice and warm. Isn't that cool? See like the bubbles forming in here? Like how cool is it? Yeah, look. It's awesome.
It's a gassy core.
So there's a hypothesis that underneath the ice shell of Enceladus, that there's this organic rich layer, and that the gases that are being ejected out of the vents, they end up forming like this sort of bubble layer. So I'm kind of like really excited about this.
You wouldn't look at that and say that's life.
Sure.
But you would look at that and you would say there's chemistry that is similar to what we think started life on Earth.
So cool.
It may not quite be going to those other worlds, but we're going to a natural system in an environment where you're just focused on the work, focused on what you're doing.
There's just so many things that you could answer about the world around you, and I am just so curious about all of those things.
I'm joined now by Bethany Teeling, a planetary geochemist. Bethany, thanks for being here with us.
Thank you so much for having me.
So we just saw you, wading through a lake, scuba diving under the water. Can you tell us what were you doing? What were you trying to find out?
Yes, so we had a lot of things that we were trying to accomplish while we were there. So first of all, we were doing a lot of work from the boat. So we actually had a boat out on the surface, and we were trying to get samples from various depths in the lake. And this allows us to go, I think we went up to like 120 feet.
Oh, wow.
So it was really deep samples that I wasn't going to go scuba diving to.
I was like, that's
time.
impressive. That's
maybe
like fast open water.
Maybe next time. But yeah, so we also collected a bunch of samples through scuba diving, and all of these are trying to get at this question of where is carbon coming from and where is it going in the system. And all of that tells us about, how other organisms might be able to use carbon. So could we have life on another planet or a moon? And then how could they use that carbon, or how could it become available for life?
So how does the science on Earth really influence how we're looking for habitable environments in other places beyond Earth?
Yeah, so this system in Iceland was so perfect because it's right along this kind of this rift zone. So you basically have kind of a fissure in the Earth's crust, and it's sort of opening up there, and you get this these hydrothermal fluids coming up. So this is like hot water that's going through rock, and it's altering the rock. And so this is not just a volcanic environment. It's also a place where you're actively changing, and that's a great video. So you're actually changing the subsurface of that floor. So you're creating new minerals, and you're creating new kinds of organic molecules, and all of those kinds of things could be food sources for other life forms.
And do we think these kind of, vents on the floor of lakes or maybe oceans exist other places?
We actually do. So we have a lot of pretty strong evidence to suggest that this is happening actively on Enceladus. Enceladus is a moon of Saturn, and we were fortunate enough to have the Cassini spacecraft ended up not only identifying that they were there, it actually flew through the plumes. So we were able to kind of redirect it so that it went through the plumes. So these are going, upwards of a kilometer or more out into the solar system. It's incredible.
Wow.
So these are geysers of water and salts and organics. But one of the incredible discoveries we made is that there's actually not only organic molecules, but also methane, carbon dioxide, and hydrogen. And all of those components together means that there's enough chemical energy to support life. We also found silica particles, and that doesn't sound like it's very exciting. So this is like kind of like a quartz crystal, right?
Yeah.
So we found like little tiny bits of these little silica particles. But what that means is that there's probably things that are altering the subsurface at depth, and then ejecting it through these vents from the upwards through the surface. So we're actually able to see that from space, and that was an incredible discovery, like all of those things together.
Oh my goodness. So on Earth, these vent environments, are they known to harbor life or, again, help life? Is that why we're so excited to be seeing these things from Enceladus?
Yeah, so some of the, there are several hypotheses, but one of the prevailing hypotheses is that, these are the kinds of areas on Earth that could have had the rise of life, right? So there's enough chemical energy and there's enough changes. So basically we're looking for gradients. So this is where the chemistry changes from here to here, or the temperature changes from here to here. So you want to have something that you want to change. And what happens across that change means that you can actually move energy from one place to another. And so we think that this is the kind of environment that could have resulted in the formation of life on Earth.
Wow.
In ancient Earth's history.
Yeah, and now we're seeing little signs on another world.
Yes.
That's amazing. Now I have one more question, but I want to remind our viewers that might just be tuning in, submit your questions for Bethany about ocean worlds and hydrothermal vents and places where, we could be searching for life by dropping them in the comments wherever you're watching or by using #AskNASA on social media. Now, Bethany, while we wait for folks to drop their questions in, I wanted to ask, how did you even get into this line of work?
Yeah, so I, similar to Emily, I have like a really weird path, but this work specifically, so going to Iceland and doing things related to ocean worlds and underwater. I grew up in Florida, so I'm Central Florida girl, and I grew up scuba diving and free diving and snorkeling with my dad in the springs, and it was just this incredible experience where we would, you take a breath if you're free diving and you dive under the water and the world just sort of falls away. And then you kind of look out and you just see there's just this totally different world under there.
Yeah.
There really is. And it is breathtaking. I mean, you have one breath, right?
Yeah.
But it is breathtaking. And I just remember this profound feeling of wow, how did this even come to be? And I really carry a lot of that with me anywhere I go. So, whether I'm in a lava tube or whether I'm doing, sedimentary geology or I'm under the water, I'm in a boat, every experience, I think there's this opportunity to look out and say, wow, how did this happen?
Yeah.
And so that's kind of how I became a scientist.
That's cool too. And I mean, being able to now apply that to other worlds is just incredible.
It is.
So let's get to some of these Ask NASA questions. I have a great question from Vivi Dreams on Twitch, who asks, what happens if you don't find what you're looking for in the field? You found your bubbles, but what happens? But what happens if you go out there and, it falls short?
That's a great question. So we try the best we can to find the right place for the right question. And there are times where maybe it's not exactly the way you expected, right? So even when we went out to Iceland this summer, we were pretty sure we were going to find specific kinds of signatures. And once we got out there, things were, that maybe we expected the temperatures to be a little bit different, and it wasn't exactly what we expected. Or the pH we thought would shift more, and it wasn't exactly what we expected. One of the great parts about this is that, these are not a loss. And I think we don't talk about that enough in science, is that having a result that's different from what you expected or your hypothesis is not a bad result. That's still good science. And so it's a really good opportunity to sit there, take a breath, and say, okay, well, what does this mean? And if I tried to come up with a hypothesis where this was the result, then how do I need to reframe my thinking about this kind of environment? So it's actually a really good opportunity. It does happen, but yeah, it's an opportunity to learn.
And it opens new questions, right?
It does. And I have so many questions now.
Yes.
Yes.
So, you were out there in the field. Did you find, again, you found the vents, but, I do know that you took some investigations. Did you get any results back from that yet?
We are just getting some results back already, so that's very exciting. Yes, I've been looking at some of our isotope data this week, which has been really great to look at. And what we're seeing, we had a couple of different areas in the lake in different depths. We are seeing that, as you go closer to the vent or further away from the vent, you're getting different signatures. So that could really help us figure out how to explore these sorts of areas on other planets and moons, right? So having that distinctive signature is really nice. We also looked at not just the Lake Klevervatten, which is this lake that we've had in the videos, but an acidic lake that was just to the south, Lake Granavatn, and those are very chemically distinct. So it was really nice to see that our hypothesis was correct, that at least they would look very distinctive. But I think we're going to start to see with all of the data, so not only do we have like the inorganic material, we have organic material, data from that coming back, and I think that by combining all of that data, we'll see where does that carbon go. So it's kind of like following it on the recycling journey, where it goes, like up through the crust. And so that's our original product, right? Mm-hmm. And then as it goes up through the crust, it gets altered, it gets used by something. It could be in the atmosphere, it could get dissolved into the water or used by some microbes. And so we can actually see that recycling through the system by using the isotopes.
And so you're talking about, you found different signatures closer to the vent, farther away. Can you give us an example of like what is a signature that you're looking for?
That's a great question. Yeah. So it depends on what you're looking at. So because I'm a geochemist, I tend to look at chemical signatures. So that could be like the concentration of something. So maybe we have more or less oxygen as we go into a different environment. Or maybe, with these isotopes, we sometimes see that it looks more magmatic. That means like coming from the magma chambers or from this, like from the deep earth. So it's coming more from that in certain areas versus other areas. So that's actually really helpful for understanding how the carbon moves around.
Okay.
Yep.
And so I have a great follow-up question actually from Batsu Z9 on YouTube, who asks, what are the signs of life in other planets to look out for? So again, kind of picture this is set on Enceladus or Europa. In your geochemical background, what are some signatures that you might look out for in the water that tells us that there could be something alive?
This is a great question, and actually a really challenging one, because it kind of gets into like an existential crisis, like what is life? and how do we look for it, right? So there are many different kinds of ways we'd look for life. So there are certain scientific groups that really ascribe to the idea of looking for particular organic molecules. So these are molecules that are formed of carbon and might have things like hydrogen or oxygen or nitrogen kind of attached to it. So they're very specific arrangements of carbon molecules, right? So certain people and groups think that that's the best way. I particularly, and this is just, my group, of course, we ascribe to this idea that isotopes can help you do this. So if you imagine, I won't go through all of the fuss of like what is an isotope, but imagine that all of the material we take up, so anything you eat, has carbon in it because we're carbon-based life forms. Mm-hmm. And so we take in this carbon and we fundamentally transform that carbon. So we also have byproducts. Sorry. But so basically, anything that comes out of us is fundamentally transformed from the original that we took in.
It's traceable.
And it's traceable. So, I joke with people that I look for microbe farts, and that's basically what I would be doing in the solar system, is looking for the evidence of metabolism. So I want to say, like, well, this is the original, and so that's why we have samples from all over, this lake, and we have sediment samples, too. We have gaseous samples, liquid samples, because we want to be able to say, if a microbe interacted with this and used it to make energy, then I should be able to see that byproduct in one of these different products. So on a different moon, so on Enceladus or Europa, for instance, then we actually could see a lot of these byproducts in just the gas, which means it's easier. We can actually do it from the surface or from orbit. We don't actually have to dive through the ice or drill through the ice in order to get there. So it might actually be a little easier. That's why I love isotopes.
Yeah. And I have a great follow-up from Tommy T on X, who basically gets at this point about, preparing to find life as we don't know it. And so, like, how does NASA plan to detect forms of biology that don't necessarily fit into our biological rule book, which you were getting into a little bit right there. Yeah.
Yeah. This is a fantastic question. So there's a whole group of people who have started thinking about this agnostic biosignature. So how do we take what we know out of that equation? I think that there are some really interesting things that people have tried to use, like complexity, so molecular complexity, because life does tend to get a little bit more complex, but that's not going to be perfect, right? Because we know that we have single-celled life forms here on Earth. So how much is that helpful? So I think there are a lot of different things that we could do. Again, I'm going to go back to, I love metabolism, because most of the way that we think about life is that everything, like life has to use, like consume energy. And so if there is something consuming energy, then as a result, it will fundamentally change its environment. And so I think that like metabolism to me, and the evidence of metabolism, which could be isotopic or it could be just chemical too. It also could be mineralogical, as you know, Mike was on here talking about earlier about minerals. There are certain minerals where you could tell that they were formed by life. Or you could see sedimentary rocks, and that there was definitely life forms that were altering that.
Yeah.
So ultimately, I think it's going to require a combination of evidence to convince people like me that we actually saw life somewhere.
Well, it's cool too that just to hear like the breadth of people that are already studying this question from all angle. And you know, we have Ya Impress on YouTube who asks, what discovery would excite NASA scientists or you over the next 10 years in this space?
Oh, there's so many. I mean, I'm a nerd, let's be honest. So anything really excites me, all of these discoveries. I think in the, you know, honestly, at this point, I'm just waiting for us to get to Europa. So the Europa Clipper mission is on its way. I was just so utterly excited. I'm so excited about this mission. And I am really excited to see what they find, because I think when we get there, the things that we are going to learn that we didn't know are going to change the way that we think about like ocean moons and probably habitability in general. So I think at that point, it's just any information about how these oceans work on a different moon. Like we had this snapshot of Enceladus, but going to Europa and kind of diving in, well, not actually diving in, but like being
studying it very closely.
Yeah, very closely. I think that is going to really fundamentally change the way we think about this. I also agree that going to Mars, like humans are Mars, if we can get there, that is really going to change the way that we think about habitability and life and how we sustain ourselves.
Yeah, absolutely. Yeah. We have Jared Banquet on Twitch who asked, you know, did your team work closely with the Europa Clipper folks?
Not for this particular investigation. However, I am part of a team that is working with one of those teams. So we actually do a lot of laboratory experiments that are trying to predict, you know, what their instruments might see when they get to Europa. So we're trying to develop not just like kind of schematic models, like, oh, if we see this, it means this, but also like mathematical models and machine learning models even. So it's really like when you get this data, could we use that to like really quickly understand, are we seeing life? Or is it just like, okay, this is like cool salt water.
Yeah, this is different.
Yeah.
Well, Bethany, I mean, the work that you're doing is fascinating. Seriously, thank you so much for being here with us.
Thank you for having me. I really appreciate it.
And thank you so much for joining us from home. Now, if you liked the clips we shared today, there's plenty more to see. So head on over to NASA Science's YouTube channel to watch the full-length versions of all the videos featured in this episode. But that's not all. Now, if you're curious to see even more of how NASA scientists explore some of the most extreme and fascinating places on Earth, be sure to check out our new Planetary Expeditions blog. It's where we share stories straight from the field. You can also follow along their adventures on X, Facebook, and Instagram by following NASA's solar system. Now, if you're craving even more stories like these, be sure to check out the Our Alien Earth documentary on NASA+. It dives into how we're exploring our own planet to help us prepare to search for life on others. It has been fantastic having you with us as we followed the journeys of some truly adventurous scientists, people who aren't afraid to get their hands dirty so we can better understand the moon, Mars, our solar system, and beyond. Thank you so much for tuning in today, and we hope to see you next time.